Now I want to talk about gas network capacities. So computing capacity sounds good, but what does capacity actually mean? I mean, usually we imagine something like the maximum amount of gas that can be transported, but it's not that easy. Transported from where to where? I mean, the end networks we look at have 100 entries and 1,000 exit points. Everything is coupled, and if you have more capacity at one point, you get less capacity at another. So it's kind of difficult. And there is a definition for technical capacity which says it's a maximum flow bounds at the entry and exit nodes such that any possible balanced demand scenario within these bounds can be fulfilled by the network. But again, while there's a nice definition, it's not unique, so you can have another set of capacities at the entry and exit points where you trade in some capacity at one node as another. Let us go first to a simpler question. Can a certain transport scenario, just one set of demands at the entries and the exits over time, possibly be fulfilled by a given network? And here I have an example. You have two networks which basically fill in 1,000 at both of the entries. The pipelines have a capacity, whatever this is, of 1,000, and you get then 1,000 units of flow out of it. So far, so nice. But now we're adding a connection. So we're adding a connection between these 2 points there, which has a capacity of 500. And the interesting thing is this doesn't make it easier. But in fact, what you can see is that from a point of the technical capacity, it makes it worse. Because now you can have that from the left entry, you want to transport something to the right exit, which would be possible demand scenario, but actually since the connection is only 500, the over transport can also only be 500, so the technical capacity actually went down. This is something to keep in mind. And apart from this, there's also the couplings to the pressure. So imagine we have 80 bar here and it goes then to 70 and to 60 bar that way, and the other is 50, 42, 34 bar. And now we connect the two. Obviously this is not going to work because we have a connecting there from 70 to 42 bar, which basically says that there is a higher pressure coming from the one side to this other, and this will limit what is possible to transport. So what we can do here is put in some active elements like a regulator or a valve to control the network in the right way. And it's really kind of a complicated thing to get it right, and there's also some old theory even for traffic networks which is called Bress paradox, which is also a nice example for you add a connection to a network and actually the capacity goes down. And this always happens if you have no full control over the flow, but kind of the flow decides itself, like here with the pressure, or if a car network, the people want to do the fastest route, and then it might be that it gets longer for everyone, or in this case less. So how do we compute these things? The correct way would to have a transient model, since we're doing things over time. This is a realistic way to do the computations. But on the other hand, you can only compute this over a finite time horizon. As I said before, I mean, you're basically somewhere in the middle always. And so if you want to compute some capacities, basically it requires a forecast of the in and outflows over time, on the one hand. And on the other hand, we need a start state for our planning. So this is kind of okay if we are talking about now, because we can just look up the start state. But if we are talking about planning, it gets a bit difficult. And if the other thing is that since we're doing computations, the deviations between the predicted and the physical network will grow over time. So if we want to decide feasibility for a future demand scenario, so for planning purposes, the question is, what do we take as a start state? I mean, we could take a worst case start state, which would basically be an empty network, which by far would be too pessimistic. All possible is impossible because it's infinitely many. And a suitable start state, well, sure, if we get a suitable state, pretty much everything is possible, so it might be likely overly optimistic. And from then on, once you have kind of a start state, you still have to see what your prediction for the future is, you assume, and there you get the same problems. So for planning purposes, actually stationary models which describe an equilibrium network state might be a better choice. So by definition, they describe a stable situation, kind of an average network state, because we have taken the time out. There's no start state needed, there's no time horizon to consider, and it ensures that the situation is always sustainable. And you need much less data. The physics is simpler, so all kind of nicer. The price you basically pay for this is that it's less precise or correct. And the worst thing is actually that there is gas stored in the network, which is called line pack. And this cannot be modeled. And this line pack helps you a lot in some kind of peak situations, which stationary modeling might be too pessimistic about. The other is the transition between certain states of the network can also not be modeled because you are in a timeless state. So these are the main things that you are missing. Basically the kind of store capacity of the network and the way the transition. But for medium and long-term planning, it's kind of the better way, or maybe the only way, because for transient you just miss the data. So as a start, let's assume we have some scenarios and want to compute them and see whether they work. Let me first define a scenario. This is basically you're given a network and the inflow and outflow demands balance out. And what we are looking for is a setting of the active elements of the network such that this scenario actually works out. Now imagine we want to see whether contractual legitimate scenarios are technically feasible. There are the following possible approaches. We can have some experts derive scenarios that are on the border of feasibility. These scenarios are then checked using stationary models, and if they are feasible, it's concluded that also all other scenarios are feasible. So this would be looking like this. So which assumptions do we put on the set of our scenarios? I mean, it looked nicely here, but actually it might be that it's non-smooth or non-convex or even non-compact. So in the end, actually the feasible area might look like this. And then it's a question whether this approach was a good one. So the assumptions we have to make on our scenarios is that they span the set, that they are convex, that they sweep around the border, and that in between there's some monotonicity. This is all assumptions which are precisely mathematical, not correct. I mean, there can be found counterexamples. Whether they are true enough to believe in practice is another question, but there are certainly some problems here. In general, there are some decisions regarding the momentum equation. I mean, we have the correct equation there, and then we can look at it analytically, discretization or an approximation. And we need some friction model. There are also different choices, and depending on what you do, there are a lot of different choices how to model just even this momentum equation. Basically, what we are interested is the border or the frontier between the technical feasible and the technical infeasible scenarios. But the problem is that this border is not unique. It's not well defined. It differs between models and methods depending on the parameters, depending on the implementation. It's more like a gray area. And this means that the one tool can say, oh, this scenario is technically not feasible, while the other tool says, oh, it's feasible. And this makes it a bit hard to decide things here. And actually, it's worse. So what I said is this is the border of contractual limited scenarios. But actually, we are not interested in the contractual limited area, but the contractual limited and reasonable area. I mean, you can always make some worst case examples where every practitioner will say, yeah, in theory this would be allowed by the contracts, but practically it will never happen because it doesn't make sense or for other things. And this area again is not well defined. And this makes it so hard to come up with a good set of scenarios. So it's all crap. I mean, this does not help us now, and we have to solve the problem somehow. So let us go and show some possibilities to generate scenarios. So here are several ways to generate scenarios. I mean, first we have to assume that we can actually create them and that we are able to check the technical feasibility. So then basically there are three methods. We can manually generate expert scenarios. This will be a limited number because it has done by humans. It will have a high quality though, and by definition makes sense. Then we can automatically generate extreme value scenarios. There it's very difficult to distinguish between contractually legitimate and reasonable or not. On the other hand, we can compute a high number of them. But possibly somebody has to look at the infeasible ones later on and says whether they are reasonable. And we can automatically generate stochastic scenarios based on stored data. There they will be reasonable, there will be a high number, and we even get a probability distribution. But on the other hand, we will seldom have extreme cases. So in the end, the best way, of course, is to combine all three methods. Then there are hardly any disadvantages left. This may lead to a huge number of scenarios, of which many are possibly similar, but then there are some ways of scenario reduction where you might get away with this. But it's clear that the testing of the technical feasibility has to happen automatically, which can be, again, troublesome with some extreme value scenarios. As I said, I mean, they are borderline, and depending on the tool, you might get the one or the other result on it. But if you can do this automatically, you can basically use to compute capacities. Okay, this leads us to the question whether to use simulation or optimization. Simulation is nice because it's very accurate gas physics models, but it relies on humans to decide the settings of the active elements. So basically you can only use it for a limited number of scenarios, and what is worse, if nobody is able to find a feasible solution, it doesn't mean there is no one. It just means there was nobody who can find one. So it depends very much on the experience of the people who operate the simulator. Optimization, on the other hand, works automatically, can possibly prove infeasibility, but then has the disadvantage that it's only working on a simplified model. So the question is again, what this gives you, as we are always interested in the border, and again, this makes the border less well defined. Now I will tell you something about a big project we had, which was the ForNe project, or the Research Corporation Net Optimization, where you can see a lot of institutions were involved, and this project ran several years, and I will show you how it ended up. So one of the goals of the project was to build an automated system that, given a network and a set of supply and demands at the border points, compute settings for the active elements of the network such that the resulting stationary scenario is feasible. So the project started basically in 2008 when I was contacted about whether we can do something, and it kind of ended in 2016 when we were awarded the Euro Excellence in Practice Award for the results. After the start of the project, at some time after about 1.5 years, we were able to solve a network like that one, which had 136 pipes, and we could solve this in 30 minutes. Then a few months later, we were down to kind of 15 seconds for the same problem. By November of that year, we had a new MIP approach and could solve a considerably larger network in about 3 minutes. Then we implemented subnet operation modes, which is kind of important because basically all the valves and so on in a compressor station are not independent, and so there's only a limited number of choices you can have. So the model got more realistic, and on the other hand, we again could solve a larger problem with this. And then a few months later, we were able to solve the L-gas network in about 2 hours, which you can see is already a vast network with 3,500 pipes and a lot of compressor stations and so on. Then another year later, we had a neural algorithm implemented and got down to about 20 minutes for the same kind of network. A few months later then, we had finally the H-gas network, which has a little bit less pipes, but much more compressor stations and active elements, and could solve this in about 9 hours. And then by introducing some special heuristics and stuff, we got this down to about 1 hour. This allowed us to solve basically the problems we wanted to solve. So here you can see a picture of not even the whole team, but quite some part of the people who were involved. And after 6 years and 30 people at 10 universities, we actually wrote a book. And if you're interested in the whole topic, get this book, and there are all the details. Gas networks give you some additional difficulties all the time, which just is a reason of being a real-world problem. Technology is changing all the time. The new systems are mixed with existing ones. It's just added to it. It's, as I said before, hard to determine actual system limits. Because, I mean, a compressor station runs there for 20 years or something. It might have been measured once, but things change over time. There are changes to the system, and it's kind of hard to get precise information. Then another thing we experienced is that optimization actually is much more prone to data errors than a simulation, because nothing evens out. So if you, for example, have the inclination of a pipeline wrong and erroneously think it's very much inclined, then the optimization model will use this as a cheap compressor in some way. And this makes it kind of hard. You have really to get all your errors out to get good results. And for larger models or scenarios, it's really hard to compare both to reality and to find all the errors, inconsistencies, because it's just complex and it's not obvious what the right answer is. And finally, marketization, this entry-exit model and so, makes it very hard to predict the behavior of the participants, since they're out of the systems and their objectives are not clear or unknown, or might be actually the outcome of a game. So it can be that some trader nominates some amount of flow, and the TSO can tell them, oh, due to a special contract, this is not a good idea. Then he can renominate at some other point. And so what actually, you have a lot of influence on things, but it might be actually the result of a game. So finally, here are some insights I got over the years, and this is basically that relevant real-world questions can be tackled efficiently with mathematical optimization and algorithmic intelligence. It's possible to solve these problems. However, a substantial effort is needed to succeed. The setup cost is very high compared to research, to pure research. You need close cooperation with practitioners, because otherwise you will get nowhere. Different disciplines have to work together and collaborate. And finally, you need access to the data and have to create, to fix it, to correct it and everything. This is really essential, and this is a major part of the work. So if you want to do this, good luck, but it's very rewarding on the one hand, but it's a lot of effort on the other. Thank you very much.